Let me start recording. So you should be able to see a Word document right now.
Mm-hmm.
Okay. So with the Word document here, the help folder, this is, of course, this is not the directions of the lab. This is just a schematic that I use for my online class to explain how well, for one, I do have my graph paper here. And I'm not showing
Mm-hmm.
the whole picture, but I'm just showing a side of it where it shows you how you're going to be labeling the axes. These directions are provided in your lab book, right? But what I've
Okay,
done
yeah.
is
Mm-hmm.
this is the graph paper I had on campus, so I have actually sectioned out the little increments for the x-axis and your y-axis. So you see that most of the graph focuses on a little bit of the x-axis, the positive side, and most of the negative side of the x-axis. Because I think on the right side, the positive side, they said go to 50. So the side that you're not seeing right here, wait, draw. The side that's missing here, let me see if I can fill it in, is negative 50, and there should be a negative 25. Of course, you have 0 right here, and then you have 25 and 50. So in the directions, they tell you how to draw your axes, how to label them, right? They say go on your
Mm-hmm.
x-axis, go from 50 on the positive side all the way to negative 300. So my spaces that I have here, my increments went all the way to negative 325. Okay, that if they're
Mm-hmm.
having you do it this way, that means that this left part of the graph is important. And then for my y-axis, I'm trying to kind of guess here. This part here that's missing is 2, and this is going to be 1. So these are the height. Okay, my units are in inches, if I can read that correctly. It's height in inches. Okay. So in the actual lab, it's a gas law lab. So the lab is about gases and the behavior of gases. So when we go through the chapter, so I'm assuming you haven't gone through the chapter yet, we're going to be talking about 3 main gas laws. The first gas law, so I'm just going to paraphrase as I write it here. Gas laws. There's 3 of them that we talk about. The first one is Boyle's law. So I am writing with my mouse, so excuse my handwriting, but Boyle's law.
Mm-hmm.
The second one is Charles' law. And then the third one is, I guess, no, that apostrophe is over there. Avogadro's law. Avogadro's law. Okay. And these are called simplified gas laws because there are more complex versions of gas laws, but these are the 3 simple ones that we go over. And so real quick before we get into this lab, when we're dealing with Boyle's law, let me see, can I write here? Oh, no. When we're dealing with Boyle's law, we're studying 2 characteristics of the gas and comparing with other characteristics. So let me see if I can write on the bottom here. With Boyle's law, so I'm just going to abbreviate here, Boyle's law. When we are studying the behavior of gases, we tend to study 4 behaviors at once. And we're trying to see how each behavior influences the other. So when we get to the chapters, you see how this plays out. We're looking at pressure, the measurement of pressure, so the pressure of the gas. We're looking at the volume. We're looking at the temperature of the gas and the number of moles. So the amount of the gas is measured in number of moles, which is just abbreviated moles of gas. Okay, so these are 4 properties all gases have. Pressure, each gas has its own pressure. Each gas tends to occupy a certain amount of space. Each gas has its own temperature and number of moles. When scientists, different groups of scientists, were studying these 4 characteristics of gases, they were trying to figure out how these characteristics affect each other. So if I change the pressure, how does that affect the number of moles, or vice versa? If I change the number of moles, how does that influence pressure? So since they were studying these four together, to figure out a direct influence between the number of moles and pressure, they decided to come up with a plan, which is, even though we're technically studying four, in order for us to see how one characteristic directly influences the other, we'll just kind of mute the other two by keeping them constant and then study the other two. So that way, when one changes, we can say it was a result of the other behavior changing. So this page is a little different because I'm used to writing on my iPad. Let me see if I can get my iPad here. Dealing with the four properties of a gas, which we said were pressure, volume, temperature, and moles. Okay, so when Boyle's the scientist was studying these four, he focused on the relationship between pressure and volume, and for that reason, he kept the number of moles and temperature constant. So these two were kept constant with Boyle while he studied volume and pressure. So he noticed, let me write this down here. He noticed, so this is Boyle's law, the volume of a gas is inversely proportional to the pressure when temperature and moles are constant. Okay? So what he's saying is when you look at the volume and try to relate this to the pressure, how do these two influence each other? So we want to keep the other two measurements out of the way so they're not influencing our results. We want to make sure we get a direct relationship. So you keep the following constant. You keep the number of moles constant and temperature. How does volume influence pressure? He noticed that we don't have a direct relationship. We have an inverse relationship. So when I was learning this back in my days, I used to call it the VIP law because it was V, then you had I. Well, it
Um,
was one. Yeah, yeah. Hey, I was a teenager in middle school trying to survive this class, and that helped me because all I had to do was put the proportionality sign in there, and I could see V proportional 1 over P. When you have an indirect relationship, right, like this, where you have inversely proportional, what that means, so the implication of this law, how this plays out, is if volume is increased, pressure is decreased. So these were the findings, right? Volume is inversely proportional to
mhm.
pressure. The implication, how it plays out, what do we observe in the lab? If you increase volume, pressure is decreased. Okay, we only see this relationship if you have kept number of moles and temperature constant, aka kept them out of the way from influencing our results. If you don't keep these constant, they will somehow influence the results and you may not see this relationship. Okay, so I'm trying to keep it simple because right now we're talking about the lab. Okay, second
Mhm.
part is Boyle's law. So I'm not going to go into all the math and all the stuff. Oh, sorry, this is Boyle's law, right? Second part is Charles' law. Charles law. So with Charles, once again, when he had four measurements to pick from, he picked these two, volume and temperature. So he noticed that, let me stick with the same format, the volume of a gas is directly versus inversely, directly proportional to the temperature. And of course, that is vice versa, right? So how do I write this
Mhm.
down? Volume is directly proportional to temperature. But remember, since we're trying to figure out how these two measurements or characteristics influence each other, we want to keep the other two out of the way. So we don't want the number of moles or pressure to interfere with this observation we're trying to make. So we keep number of moles and pressure constant. Okay, keep them occupied somewhere, constant, not changing, not influencing our results. What is the implication of this observation or this relationship? The implication is if the temperature of gas is increased, comma, volume is increased. Since they have that direct relationship, they change towards the same direction versus here we had that indirect relationship, right? Or inverse relationship. So when
Mhm.
one factor increases, the other one decreases. So they have the opposite trend. Here we have same trend, same direction. Okay. And
Mhm.
the last one I'm going to talk about is Avogadro's law. Avogadro law. So he related the volume to number of moles. So out of the four he could pick from, he related volume to number of moles. And essentially he says, let me see, sticking with the format, the volume of the gas is directly proportional to the number of moles. Okay, so if I'm to write this down, volume, number of moles directly proportional. What do I keep constant? The other two, keep them out of the way. So we keep these two here, pressure and temperature. Okay, so once again, what is the implication of this in the lab? Implication. If number of moles increase, comma, volume of gas increases. Okay, this is as simple as I can explain these three laws. I didn't go into the math. I'm trying to keep it simple to help you finish
Mhm.
the lab. Okay, so one of these laws is being illustrated in your lab, either Avogadro's law or Charles' law or Boyle's law. One of these laws is being illustrated in the lab. So now that we've seen these laws in the background, we're now going to see how this works in the lab. So now we're looking at the lab. Oh, I just realized something. This is in the actual lab protocol. Somewhere here on my desktop where I have a lot of junk. It's a lot of work. I do have the lab instructions.
Yeah.
So what I'm showing you here is just once again, oh, I did show you the actual paper right here. Okay. So let me see if I can find the actual lab
Yeah,
instructions.
that's what's. Mhm.
And then we can talk about this part here. Because the instructions and then what I remember are not always the same thing because I just kind of paraphrase. And you have the actual instructions. So I think I have it as Chem, hold on, Chem 1405 online. Yeah, there it is. Yeah, so you have the hard copy, right? hard copy book?
Yeah, because I think it's experiment 3,
Okay, experiment 3. Okay, let's
or
see. I'm waiting for.
I believe that's what it is.
Okay, yeah, I'm waiting for this thing to download and it's not.
Well, actually, that might.
I'm trying to see if I have a version of it somewhere here. Yeah, because what I have right now is the gas law help. Okay, I tried to click on. I thought I clicked on something, but it's not showing. There it
Oh,
is.
it's.
What is it?
Oh, I guess it's actually experiment 10. I think it's actually experiment 10.
Oh
Because
yeah,
that's.
yeah. Okay, so the the order in the lab book doesn't necessarily match the order in
Okay,
the
that makes sense. I was
yeah,
like, what is that?
because the
Okay.
lab book was made at a different time when this book was used, so we just we're trying to match it to the textbook versus the other way around. Okay, why is this thing not opening?
Mm-hmm.
Come on. I saw it somewhere here. This is not what I'm looking for. Because oh, there it is. Oh, so it's open this whole time. Yikes. Okay, there. So it said lab 10, right? Yeah, gas laws, and that's your page
Mm-hmm.
number 42. Okay, so somewhere on the
44.
bottom. Oh, okay. So you see that's the other issue. I have a different version. Mine is not the updated version.
Oh, okay.
Yeah, so you see what I see right here, correct?
Mm-hmm. Yes.
Okay. Okay. So okay. So here under ordinary conditions, yeah, it talks about all this is all the background stuff. So you see, it tells you Bohr's law, Charles' law, Avogadro's law, and the perfect gas law. The perfect gas law combines these three. Okay. So I didn't really go over that part, but I went over the Bohr's law, Charles' law, Avogadro's law, right? So you can see that part. Then they go through here
Mm-hmm.
and in their own way, they talk about what Bohr's law is. I kind of showed you that already. In their case, they made the subject the pressure. Those two variables are interchangeable. You can start with the pressure or start with the volume as long as you have them as inversely proportional. So they have that part there. They go and do the maths to get this form right here. Okay. So they do
Mm-hmm.
go from the proportionality relationship. And this is equation number 1 is called an expression because there's no equal sign. And then equation number 3 is called an equation because you do have an equal sign. Okay, can I write on this? No, this is signature. Okay. So they walk you through how they go from the expression all the way to the usable equation and all that stuff. We're not doing all that stuff right now. Finally, here, experimental procedure. So it says obtain the following items: transparent or translucent drinking straw. Either one is fine as long as you don't have a metal drinking straw that you can't. We have to see the liquid, right? We have to see the liquid level.
Mm-hmm.
So you want either a transparent or translucent straw. The picture I showed you, my straw was mostly translucent, not as transparent. And you want it to have an insert diameter of approximately zero point 0.4 centimeters. I just grabbed this straw, the first thing I saw, and that was good enough. Okay.
Okay. Mm-hmm.
And, right. So a standard straw you get from the dollar store or Walmart, whatever you have at home should work. And then it says food coloring. The purpose of the food coloring is to color the water because we want to see the level of water inside the straw. And then here they talk about a votive candle. I did not use the candle. We tried the candle one time, me and my coworker, another professor, and we struggled to get the plug. So then we came up with an alternative. Actually, somebody else did, which is to use gum. So if you're gonna be using
Yeah, I saw
gum
that.
to yeah to plug the hole, then you don't need the candle because the gum makes up for the candle. The wax is just to be able to plug that hole and trap the gas. So if you're not going to be using the candle, then you're going to be using gum instead, right? And so when you start your experiment, you want to start chewing the gum. You want to chew the gum to
Mm-hmm.
make sure it's sort of hard, not very, very hard, but not very soft either. If it's too sticky and too soft, it will stick on the bottom of the cup, but you want it to remain firm. And then here they tell you salt, ice, thermometer from your kit,
Okay.
a ruler, graduated in millimeter. A ruler whose height, who which is graduated for you to be able to measure the height and stuff like that. Then styrofoam cups. The binder clip is unnecessary if you're not going to be using the candle wax because the binder clip was supposed to
Okay.
hold up the straw for you to hold it erect or vertical so that you can pour the wax into the straw. But if you're not going to be using the candle wax,
Okay.
you can just go ahead and hold the straw with your left hand or right hand, depending on what hand is dominant for you, and then use your chewed gum to press, use your other hand to grab your chewed gum and press it on top. Okay, so here it says fill one styrofoam cup with water within 2 inches of the top and add a few drops of green or blue food coloring. Okay, so what I'm going to do is here is I'm going to divide the screen into two. Okay, yeah, excuse all the pages. Whenever I'm working on stuff here, I have a lot of pages open. This is just my life.
Yeah.
This as a chemistry professor, I have to have a lot of resources with me at all times. This is just a life. So I tell people I don't get to have one of those neat office tables because that's not
Yeah,
practical.
there's just so much.
Right, right. I need a lot of resources. So on the right, I'm going to have my iPad. And what I'm going to do is translate what they're saying into action. So we're number two right now. We have a styrofoam cup with water, and you want to fill it within 2 inches of the top. You want to when they say 2 inches, I don't know. It doesn't hurt to fill the cup to about 1 inch from the top. It's really it all depends on you. But let me try to stick to what they're saying. So here's my cup. Well, hold on. Sample number two. Here's my styrofoam cup, and we have water. Because I've tried it on campus where 2 inches from the top was not deep enough because it didn't tell you what size of styrofoam cup, right? On campus,
Hmm.
we have large cups and small cups. When we use a small cup, the liquid in here was not enough. So I would say, just to be safe, add a lot of water. Not all the way full, but I would say about zero point 0.5 to 1 inch from the top. While they're saying 2 inches from the top, that was because I think they used a very large styrofoam cup. If you have a smaller one, you will see that in the end it doesn't really work very well. Okay,
Okay.
so you have water in here, and then you added blue or green food coloring. Add a lot of coloring to make the water dark. So add coloring, so as many drops as possible to make water dark. Okay. And then while we're here, still on number two, you have a drinking straw, right? Now on campus, when I did this lab, my drinking straw was the one that had that bendy end, that's kind of like this and it bends like this. You don't want that as part of the experiment, so you want to
Hmm.
cut off 5 inches, 5 inches from the end to here. Mark it and then cut it off.
Okay.
Okay. And then here is saying shave a large flake of wax off the candle. We're gonna skip that part. So here we start chewing gum. So start chewing. Chew away. Number three, chew gum until firm. So when the sweetness has left, when you start feeling, all the sweetness is gone, all the flavor is gone, then it should be firm enough. Okay. I say that because when you put the gum in the hotter water, if it's not firm enough, it will actually become a lot more sticky and then stick to the bottom of the cup and then pull the plug out and then you're done with that tape. You have to start over. Okay, so if anything at all, it's better to have the gum too hard than too soft. Okay. Where are we? Number three is
Okay.
done.
Hmm.
Number four, it says pack all this stuff. Yeah. So we're skipping number four again. So here you're gonna. So for number four, it says pack this. Okay. So you're packing the flaked wax into one end of the straw. I see what it didn't say. I didn't really realize this. So you want to place your straw vertically in your cup, the cup that you had up here. So you take your
Hmm.
straw, hold your straw vertically, and place it in the cup that had the colored water. So you want to place your straw all the way down. So to illustrate that here, all the way down. Well, yeah, as low as possible. And when you do this, when you hold your straw vertically, you will have some of the liquid inside the straw, let's say to about a similar level to the outside. Okay. Then at this point, you take your chewed gum and put it on top like that. I think that's what I had in the picture right here.
Yeah, I do.
Right. So you want to make sure your straw is in the cup with the colored water before you place the gum on top. Because the purpose of the gum is to create a gas pocket. So here you have the colored water, and then between the colored water will act like a plug. So this would be a water plug, preventing the gas from escaping. Water plug to prevent trapped gas from escaping, right? And on the top, you have the gum. The gum is acting as another physical barrier. So what we really care about, we don't really care about the gum or the colored water. What we care about is the trapped gas in between these two, because this is a gas law lab. I have to keep stating, remember the purpose of this lab. We care about the gas. Right. Because sometimes students will get confused and then they'll kind of, because it's kind of a means to an end, and we're detouring to try to get gas trapped somewhere. Okay, so once you have the gum on there, you want to press it nice on
Hmm.
the edges, not too hard, but nice enough. And then you want to pull the straw out of the water. When you pull the straw out of the water, you will hold the straw out suspended in the air. And if you have a good seal, like a good seal in here with the gum, then the water will not leak. It may kind of drop a little down here and it will look like it's about to leak, but it will not leak because there is sort of a vacuum, not really a vacuum, but there's a suction created that is holding the water in place. If you pull the water out of the cup,
Okay.
oh sorry, the straw out of the cup and it leaks, then you did not create a good seal up here. And the issue is the seal. You want to put it back in the water until you get a good seal. So this is the device that we're going to be using to do our experiment. All this was to create this part right here. So you want to have your gas here trapped between the water plug and then the gum end. So here, step number 5 is when they're telling you to pack the wax on the, yeah, this is just a lot more steps. The binder clip is to hold this up. You don't need all that. And then lower the clip, light the
Yeah.
candle, all the stuff is required. Fill the plug until the liquid starts to overflow. We're not doing all that. Allow the wax to harden. The gum is already hardened. Okay, finally, by doing that, we can skip and now go to step number 10. Look at how much we skipped. So now that we
Yeah.
have taken this out, right, and we can see that the plug is going to work, now we're trying to expose our gas to different temperatures. So here it says rotate the straw 180, flip it over. So rotate straw. So what I usually do when I'm reading directions is I write it out in my way. Like I write it out in a way that makes sense to me. It says rotate straw 180. Rotate, or I can say here flip. And I try to draw pictures because that makes more sense to me. So my straw will go from being held like this to being flipped where I have my liquid end on top. So here is where I have my liquid end, liquid end. And then of course I have my trapped gas and then my gum. So I try to draw this somewhere in the help folder, right? Flip it over
Mm-hmm.
there, right?
Yeah.
And then these are three different cups from the top cup. So in the end, you're going to have four total cups. This one here was just to provide you with the colored water inside the straw. So we are done with this. As long as your straw doesn't leak, we're done with the first cup. So here we have three different cups with three different temperatures. Okay. So back to the one that I'm drawing now, I'm gonna have three different cups. One, two, three. Excuse the cup getting small. I'm running out of space. And so let's see. Rotate the straw 180 so that the open end is up. When they say the open end, I know. Here's the thing. With chemistry, you kind of have to read between the lines, and that's the issue. That's why I have a job, right? Even the online class, I can't run an autopilot because when they're saying the open end, you're like, wait a minute, there is no open end, right? One end is a liquid end, the other end is a gum end. From my point of view, both ends are plugged. So what do they mean the open end? They mean the liquid end. So rotate the straw 180 degrees so the liquid end is up. And then the other end, the one with the solid plug, the wax plug, in our case, the gum plug, is down. That's why I do the picture to help you out. The water plug should remain in place and not drain on top. Oh yeah, we checked to make sure that seal was tight, right? We want this seal here to be tight. So what we're doing, the reason why we flip it over,
Mm-hmm.
we want our gas to be fully immersed in water. That's why I told you guys earlier, make sure this pocket is not too long. If it's too long or too high, if you didn't fill your cup enough and it's too high, say this is all the liquid you have and all of this is gas. If you place it inside this container right here, and then only the top part is liquid and all of this is gas, you will not get good results because if you notice here, only half your gas is in the water. You want all your gas to be fully immersed in the water.
Okay,
Because
that
the
makes sense.
water is providing the gas, all the gas molecules, a specific temperature that you have picked. So now they're telling you prepare three different water samples. One should be moderately warm tap water, whatever that means. Okay, so I guess this would be warm water. Then this one here will be cold. Let's say room temperature. Because when they say cold tap water and a mixture of ice and cold tap water, you're like, wait, what? Okay. Room temp. They want three different temperatures. So warm water, warm tap water, room temp water, and then ice and cold tap water. Okay. So sometimes some people add the salt to the ice or whatever. If you're wondering why we have the salt, sometimes it's added here. The salt and the ice and the cold water. But the idea is cold, room temperature, and warm. Okay, then they say beginning with the moderately warm tap water, immerse the straw for 5 minutes. So you want the straw, once again, the ideal scenario is where the colored liquid occupies enough space where all your gas is inside the water. So you want to make sure that the gas portion of your straw is completely immersed underneath the water level. So like this, okay? Same thing here. Make sure you have enough water here to have the same scenario, okay? So the gum ends in the
Mm-hmm.
bottom. and then the liquid ends on top like that. Same thing here. So you're taking the same straw. Now, when I'm drawing like this, I'm kind of getting ahead of myself. Begin. So we're doing this for 5 minutes. So for 5 minutes, you hold this with your hand because you don't have a paper clip. You're holding this. You can kind of suspend it slightly above if you don't want the gum to get stuck on the bottom. Because if your water is too hot, the gum will get stuck. It will get stuck and get stuck on the bottom of the styrofoam cup. You can hold it slightly above. You probably get tired, but at the end of the period,
Yeah.
use the black Sharpie to mark the bottom of the water plug. So the water plug will move because as the molecules in here gain energy, they will change the space they occupy. If they occupy more space, they will push the liquid out. So if they occupy more space, you see some of the liquid coming out and it will pour into here. That's okay. Don't worry about it. If some of the liquid comes out, or the if they change the space they occupy so the liquid drops even lower, you when the experiment is over after 5 minutes, you will mark the new position of the bottom of the liquid with a Sharpie, like right here. Okay, let me make it a different color. This is the new
Mhm.
position of the water plug. Now, I'm not giving you the right answer or the wrong answer. I'm just giving you a made up answer. Say that's the new position right there. Okay.
Mhm.
And drop to that level. Okay. You mark it, and then you can write on here with the Sharpie W, right, for warm. Okay. And then it says raise the straw from this water, measure the distance between the black Sharpie and the top of the water, the wax plug. Okay, so this part here is it's up to you how you want to measure this. They're saying measure this part here all the way to this end. We know that the straw was what, 5 inches? So you can measure, because they're telling you to measure this bottom part from here to here. You can measure this height here if you want, or you can measure the top height if you want. Either one works. It's up to you. I personally think that this height here is more consistent, not the liquid, just this end here. So I would say measure the liquid height. So the height of the liquid right here. And then remember, the length of straw is equal to length of the liquid plug plus length of the gas. So if you measure this, either one, if you chose to measure the length of the liquid in the straw, or you chose to measure the length of the gas, you're going to need ultimately, this is the number that we need right here, the length of the gas inside that straw. Okay. So if you measure this one directly, let's say, because I know the straw is 5 inches, let's say you measured and you got this at 2 inches. And of course, this one here will be 3 inches. If you measured this directly, you will have it as 2 inches. If you didn't and you measured the liquid directly, you have to figure out what the gas is. Just keep track of what you're measuring, right? So say you measured the liquid, you're trying to figure out what the gas is. Of course, the gas will be 5 inches minus 3 inches, which will be 2 inches for this one, right? Just the difference between the two. And then I'm going to fast forward real quick. You will
Mhm.
write the height of the air plug. They want only the air, not the liquid. So for my made up example here, my first one will be 2 inches. I have to write the gas, 2 inches. And then at some point, they'll tell you to measure the temperature. So where was I? Raise the straw, measure the distance. We did that. Also measure the water temperature, right? You want to measure the water temperature. So here you take your thermometer, measure the water when the experiment, right when you're done, 5 minutes, the temperature of the water, and then you write it, measure it in Celsius and write it down here. So let's say I have 2 inches and the temperature was warm, so let's say 35 degrees Celsius. That goes right here. Then here it says take the same temperature in Celsius converted to Kelvin. course, you know you're going to add 273, right? So as far as the table is concerned,
Mm-hmm.
for your
Yes.
warm, you have 2 inches, right? For the height, temperature, which I just made up right now, 35 degrees Celsius in degrees Celsius. Kelvin, it'll be what? Let me see. I have a calculator here. I am not doing head math. 273 plus 35, 308 Kelvin. Then here they want you to get the height over degrees Celsius, then the height over Kelvin. You want to write these numbers in decimal form because it will help you see the relationship better. So height over degrees Celsius, 2 divided by 35.057. Height over Kelvin, 2 divided by 308.0065. Okay? And so you will repeat this for
Mm-hmm.
the other two, yeah, with the same straw. You don't want to make a new straw because if you make a new straw, you bring in an added variable. We don't want the variable. We want to see the same gas, how that same gas behaves in an environment that's warm, cold, and ice cold. Okay? So the same straw. So you're done here, right? You measure the temperature, and then it says, while immersing the straw, be sure not to pinch or deform, as this may cause the water plug to drain, right? Be gentle. I don't have a gentle grip at all. So it's like, be gentle so you don't squeeze too hard. If you squeeze too hard, you just have everything spill all over, and then you have to start from scratch. So you're going to repeat steps 11 using the other two water samples. Using the same straw, right? So that they didn't
Yes.
specify
Mm-hmm.
that. As I'm talking through this, and since I've had real life experience for this, I'm like, there's a lot of things not said here. This was written by a man, not to say, right? If I wrote it, it will have a lot more words. But yeah, you're using
Yeah.
the
And then,
same straw, huh?
and I guess for the, so for what you want, do you also want the data table?
Yes.
Like, do we just send you a picture of that, I guess? And
Right,
then,
right. You can do a picture
okay.
of it or however
Okay.
way you save it as, and then you send it to me. Right. Yeah, the data table is necessary because you're going to be making conclusions from that, and it's part of your data. So when you're submitting lab work, the data table is part of it. Directions are not, but I won't mind if you send the directions. But anywhere where you write anything has to be submitted.
Okay. Yeah, I just
So
wasn't sure because I know with the other ones there was copies of it, so you could just print it out and fill it out. But
okay,
I
I
also
see.
have the manual, so I can just do that and then just send you a picture.
Right, right,
Okay.
right. Yeah, if you do a screenshot or whatever, however way you submit it to me, you can do it that way, or a picture, as you said.
Okay.
So you're using the same straw you made. That wasn't clarified here. The very same straw you made. You're going to be repeating the steps we just did for, it says here 10B and C. I see a typo. It's supposed to be 11. 11B and C, right? Your other two water samples. So use
Mm-hmm.
different color markers, you're not starting from scratch. Same straw. Use different color markers to mark the position of the water plug in trials B and C. So let me see. Back to what I had here. So I use on the right, I use a black marker. So I'm gonna try to simulate what they're saying. Say I use a blue marker for my other color, and then a green marker for my third color. Okay. So then I just did what they're saying in number 13. Okay. You have three
Mm-hmm.
different marks. And you want to make sure you know what color went with what trial. And then in each case, either you're measuring the direct height of the gas, which would be from here to here. This is height of gas. Or the reason why I don't like measuring the height of the gas, the gum is not consistent, right? It's lumpy. If you chew gum well, it will be lumpy. So you might get different heights and not consistent height. but I feel like the edge of the straw up here will be consistent each time. So if it were me, I will measure the height of liquid, and then do the math to figure out the height of the gas. Because people will get different answers because they're measuring different sides of the gas, oh, sorry, of the gum or the wax. If the wax is not
Mm-hmm.
flat down here, you get a different height each time because you're adding the height of the wax. But from here to here, you get the height of the liquid and then subtract, take the 5 inches minus height of liquid, and you get height of gas. So height of gas will be equal to 5 inches, which is a straw, minus height of liquid. You can use inches. I use inches because I'm like, well, we already measured the straw in inches. I don't want to do a conversion. If you want to use millimeters, you can do that too. It's really up to you. So yeah, so once you have that, that's pretty much the end of the experiment. And it says record all the data in the table below. You're doing
Okay.
only one trial. They only ask you for one trial. Take it out. Make sure trials your liquid. So you're gonna put the same straw once again, down
Mm-hmm.
in the tank over here. Yes, ice water coloring. And this is supposed to be the thermometer. Here, same different condition. And I told you, yeah, height of gas is straw height minus height of color liquid column. So once you're done with that, you're gonna have these numbers here, then these numbers here, and then let's see what they say. Oh, look at that. Question number 16 tells you which law we're looking at. Charles' law, right?
Mm-hmm.
Right. So number 14, use Excel spreadsheet. You can draw the graph manually like I did, or you can use Excel spreadsheet to plot the height, this height here, as a y-axis versus degrees Celsius x-axis. So even though you have temperature in Kelvin here, you're drawing height versus Celsius. Height, which would be your x-axis. Sorry, y-axis is your height. X-axis is Celsius right here. And this is where the lab help came in because I drew that somewhere here. Right. I showed you how I got well, I showed you the picture after I got my gum plug. This is a huge wad of gum. But you see how it's not level up here, right? That's why I don't like to
Mm-hmm.
measure height. I measure it from here. When I'm measuring my height, I measure it from here. After it's been in the water, from here to here. Whatever this height is, that gives me the liquid height, and then of course 5 inches minus that gives me what I was unable to measure right here. Okay, so let's see. I drew this manually. I prefer to draw it manually, old school like that. So they said from the x-axis should be from negative 300 to 50. Well, I went to negative 325 to 50. I went beyond that. But they said the x-axis should be temperature. Yeah, temperature in Celsius, x-axis. Your y-axis should be height. Since I stuck with inches, I said here inches. I have 1, 2, 3, 4, 5, 6. My increments, my spaces in here have to be the same. They have to be constant. Okay. And then it says, from the graph, estimate the temperature at which H goes to 0. So I'm just going to pick some random answers, right? Some random points. This is not the answer. That's my disclaimer. If I get an answer
Yeah,
like
no.
form. No, I'm gonna post this so others will get a chance to hear what I'm saying to you.
Mm-hmm.
Yeah, this is completely fake. Okay, I can tell you right now, it's not the correct one. So say, because in this, let me tell you how wrong this is. I'm giving data points here that are negative. We never did anything in negative temperatures, right? This is super cold. All our temperatures are mild. Room temperature, cold, and then warm. So this is completely not true. But I'm just showing you this to show you how you deal with this. We have three data sets, right? You're supposed to draw a straight line. Oh, they don't say all that. When you have three sets of data like that, you're supposed to draw a straight line. So I have a ruler here to help me draw a straight line, but I don't have a ruler here with my mouse. So to draw a straight line, it's gonna pass through here. I'm doing the best I can, like this. Okay, so based on this fake data I just made up, let me try to get this. I don't have a ruler because I'm using my mouse. Let's say this is the first data, second, third. This will be my best fit line. Okay, so after my best fit line, I'm looking over here and I'm saying, oh, for number 15, from the graph, estimate the temperature at which H goes to 0. H is from the y-axis, right? So from mass, y is 0 on the x-axis. So look at where your line crosses the x-axis. In my case, this is where the line crosses my x-axis, right? My plotted best fit line. It crosses the x-axis at, this is 100, 125, something in between the two, 25. Half of 25 is what, 12 and a half? Wait, calculator again. 25 divided by 2, 12 and a half, right. So it looks like this point is 112.5, right, degrees Celsius. Once again, this fake number is completely wrong. So I can then say, from the graph, I can estimate the temperature at which the height goes to 0 as positive 1. Can I write here? It won't allow me. No, it won't allow me. Okay. 112.5. That will be my answer here. Hold on a second. Where's the fill? 112.5. Oh, there. Celsius. There. Okay. Based on what I got from the graph. And then it's telling you the value of H over K should be approximately constant, which verifies Charles' law. Explain this result. Wait, we just learned Charles' law. Charles' law didn't say anything about height. And what is K again? Okay, so here's where, let me bring up my iPad to explain that for a second. It's just because we didn't get into the math portion of Charles' law. But since we know it's Charles' law, I'll pick up where we left from on Charles' law and add to it so you can understand how this works out. Charles' law. Charles' law talks about volume and temperature, right? So I'm going to add to it to help us get to that conclusion. So Charles' law said the volume of a gas is proportional to its absolute temperature. So I need to add this word, absolute temperature. What does absolute means? This is temperature measured in Kelvin. Okay? Kelvin. What does that mean still? That means that the volume of the gas should be proportional to temperature, but it will be only the temperature that's measured in Kelvin. The volume of the gas is not proportional to temperature measured in degrees Celsius. Okay, we get that. But then when we look at this here, I'm going to say we measured height, not volume. So we're going to step back mathematically and see, how does volume relate to height? The shape of the straw was a cylinder, right? So I'm just focusing right now on the trapped gas portion. The trapped gas has a volume that's essentially base area pi r squared times height. Okay, we're not going to try to calculate the volume here. I'm just trying to show you how the volume magically became the height. Mathematically, based on this, the way the experiment is set up, the volume is equal to pi. Pi is a constant measurement, right? It's a constant value all the time. Since we're using a straw whose radius is not changing, in this context here, the radius is a constant, right? Remember earlier when we were trying to get rid of certain measurements or try to keep them from influencing what was going on, we made them constant. So I'm going to try to paraphrase here. The constant numbers can be overlooked to see the relationship of the changing numbers. So this is what I'm about to do, and this is the rationale I'm using. Okay. Sometimes we make things constant because we're trying to overlook them on purpose. So in this case here, in this experiment, pi is a constant because pi is a fixed number. It doesn't change. But in this experiment, the radius of the straw when it's designed, has a fixed radius. So radius is constant, pi is constant. So technically, what we're saying is the volume is equal to constant times height, or you can just ignore the constant completely and say the volume is the height. So this whole time we weren't aware of this. Well, I was aware, but y'all weren't aware of this, that the height represents the volume. So you can go back and look at this experiment and see it as where it says height, you can look at that as volume. The volume is representing the height. And over when it says height, you can look at that as volume. If don't change the don't change the labels they use in the experiment. Just relate it to that. The height represents the volume. The height represents the volume. Now, how can we look at this and see this is actually Charles' law? Okay, so we're saying here volume is directly proportional to temperature as long as it's measured in Kelvin. What I didn't show you guys before is this is an expression. To make it an equation, this is what we do. Replace proportionality sign with equal K, where K stands for a constant. Uh-oh, there we go again with another constant. So all I'm doing here is volume equal constant. So I replace this part here with that part. You see that? So volume equal constant temperature. So when we rearrange the equation, we're trying to figure out what is constant. So volume over temperature, temperature has to be in Kelvin, equal K, where K stands for constants. So we did all this math, all this illustration here just to say, in Charles' law, the volume of a gas divided by the temperature. Ooh, if I can spell temperature, temperature in Kelvin is constant. Okay, so because of that, we get this equation. Volume 1 over temperature 1 will give us constant, right? Volume 2, a different volume over temperature 2, same number we had here, constant. Volume 3 over temperature 3 will give us the same volume, number constant. Therefore, we write the equation like over temperature 1, 2 over temperature 2. And then when we need to do math, we use this equation. So by Charles' law, this is a proof of Charles' law. We have Charles' law. If you take the volume of the gas, which remember in this context, the volume is represented by the height. They didn't want you to do a lot of math. And relate to the temperature, only the Kelvin one will produce a constant, not the one with Celsius. So when you work this out in the math right here, the height over the temperature in Celsius, this will not be constant. This one here is supposed to be constant. Where was I? Does that help answer your questions?
Yes, that does help because I was going through the homework, and some of the math here is what was in the homework. So this helps kind of understand because I was just going through like the hints and getting the answers, but this makes me understand like the whole a little bit
Right,
more.
right. And so if you notice, right, when you're working on the, even though you have this, oh, I'm writing again. Hold on. Bad habit. I have to make sure what I'm seeing is what you're seeing. Okay, here. So even though this is the equation that we use for Charles' law, this was the struggles I had when I was learning chemistry as a student. In math, when you have an equation, the equation you have, you usually just plug in the numbers and then everything just works. It doesn't work that way in chemistry. Just because you have an equation, because chemistry data is acquired from a lab, the units of the data may not match the units required in the equation. So in this equation here, temperature 1 and temperature 2 must be in Kelvin, Kelvin units, or else this equation doesn't work. So if they give you a question and temperature 1, temperature 2, and Celsius, you have to convert degrees Celsius to Kelvin. If it's in Fahrenheit, you have to convert Fahrenheit to Kelvin. This relationship, this equation only works if the temperature is in Kelvin. So I took math before I took chemistry. I got to chemistry. I'm like, what in the world is this? Shock, major shock, trying to reconcile, irreconcilable. Then I had to kind of create a mental space. This is a space in my mind for math. This is a space in my mind for chemistry. Not the same thing. We're using math, but we're not using it the same way, right? So when I have students come and tell me, well, chemistry is basically math, I'm like, no, take that back. No, it's not. It's not. It's not. We use math, but it's not used in the same way because people who are true mathematicians come to me and tell me, you guys are using the math all wrong. I'm like, right, you get it, right? We're not using it like you guys do in math. And they get very upset at me. I'm like, wait, I'm not the author of this. I'm just illustrating this stuff to you. Right. But we do use the math as a means to an end, but we do it not completely, but mostly differently from what is done in math. Yeah, so the temperature has to be in Kelvin. So with the other one, with Bohr's law, let's see. I guess quickly the combined gas laws. When you combine all the three gas laws, you get P1, V1 equal P2, V2 over T1, T2 here. So when you take this top part out and you get P1, V1 equal P2, V2, this gives you the equation that you use for Boyle's law. That's why they call this the combined gas law. And then from this, you can take this diagonal relationship here, take it out, and you get V1 over T1 equal V2 over T2, and that gives you Charles' law. And then from this combined gas law, I add the number of moles here, even though in the book the number of moles is not added. As a student, I was like, listen, I'm going to do what I can do for myself to help me survive this. So what I did was I added the number of moles here. Let me take this out. I added the number of moles on the bottom, number of moles 1, number of moles 2. So that helped me get Avogadro's law from the same, well, from my version of the combined gas laws. So from here, you can see the V and N relationship, and then the V and N relationship. So V1 over N1 equal V2 over N2. And this is Avogadro's. Okay. So this one here, T has to be in Kelvin. And this one here, really, you just have that. Any questions? Any other questions?
No, this is really helpful. Thank you. Yeah, that's what I was just trying to understand, and that makes sense now. I'm kind of going through all of this.
Right. I try to go back to the actual lab because when I'm teaching, since I do have outside of the lab, beyond the lab experience, I kind of know where they're going, and so I know how to get there based on what they're saying. And by going through the lab, I'm realizing that a lot of things were implied and not clearly stated. So without really, which I'm glad you did say something. And the issue is that the other video got deleted. I'm not happy about
Yeah.
that because I didn't save it, and so I have no way of finding it. I get why they deleted to create space because if Blackboard has too much stuff, it runs slowly and has a lot of issues. And I was having a lot of issues last week. Since they cleared, I've been having less issues, and I was like, oh, they fixed the issues, not realizing they deleted my videos. I have to re-record them. Yeah, so yeah, the video wasn't even a year old. Yeah, I panicked and I called a friend. I'm like, do you know what they did to my video? It's gone. Yeah, so I have to find a way to export these videos and keep them somewhere else or keep re-recording them as needed. But
Yeah.
yeah.
Yeah, because I just find them helpful. That's why I was looking for the other one for chapter 4.
Okay, well, I mean, I try to be available during this time, this afternoon time. So anytime you need to pop in, you don't have to stay the whole time. If you have a 5-minute question, a 1-minute question, just pop in. We can talk about
Hmm.
it, and I record it and then make it available for it helps everyone, not just you, right?
Okay.
Yeah. So do you have any other question? Is there any question you worked on the homework that you weren't sure of? Because just because you get it right doesn't mean you know exactly why you got it right. Sometimes you guess A, B, C, D, and then you get the last one right eventually. Is there any question in the homework that you want me to clarify?
Um, no, I think I need to go through the PowerPoint one more time and the
Okay.
video, and I think I'll understand it because I was because they do work it out to where if you
Okay.
get it wrong, so I was able to work out and make sure I got the correct answer, but I just need to go back to the video and make sure I understand it,
Okay.
which this was helpful. So yeah,
Okay.
but I'll
So
definitely
yeah.
hop on if I have other questions.
Okay, so since I'll be here again on Monday afternoon for you guys, I usually have other classes too. So if you email me and they haven't popped in yet, I'll just email you back. Because earlier when you emailed me, I was waiting on my earlier class, my general chemistry class, for someone to show up. So I was able to email you at once. If I'm in class, I may not be able to email you instantly or in a meeting. But yeah, as you're going through the video, if you do have any questions during the video, just write them down, and then of course you can email me, and then if I don't have anything going on, we can still get on like this and then do a session.
Okay,
Okay.
sounds good.
Okay. Yeah, I think the video I posted, I did work through some extra examples, so that should be helpful, hopefully.
Hmm.
Okay.
Okay, thank you.
Okay, you're welcome. Have a nice day.
You too. Bye.
Okay, bye.